Good evening, guys. I have another video that, excuse me, that I want to go over with you. I think will be a good supplement to the ones that I posted already, and should get us really kind of all set up for Chapter 10 now. Be all set, and any other things we talk about tomorrow or a Monday when we have the review for our upcoming test, we can just focus on working on examples or explaining any kind of misconceptions explaining any misconceptions that might have propped up throughout all of this. Okay. So I'm sorry. I'm distracting myself. I'm looking at a few things. But let's just go on. Let's show you what I have up here right now. Polar equation, cosine of kt. So whatever. I don't know. What's kt right now? What is k? One of these are k? I don't remember. But in any case, I think I might have misspoke that. I think k, so I think this is cosine 2t. R equals cosine 2t, and I can show you that with a Desmos. So let's double check here. Desmos, and show you how you can do polar graphing on Desmos. Desmos is really straightforward. You could literally just type in R equals cosine of 2 theta. And there it is. And yeah, and that's what we got here. Cosine 2 theta. And oh, I keep doing that. I keep messing up my... There. Do this. And you know what else? I mean, this isn't that helpful. Let's show you this in Desmos also. You can go in here, go grid. Oh, nice. And then, you know what, instead of 10, let's go like something like, I don't know, negative 3 pi to 3 pi. Oh, I guess that's okay. Maybe I don't want to do that. Here, let's see. Maybe we'll just do negative pi to pi, at least for now, and then same thing here. Let's zoom square. Okay, let's do that. And usually there's Braille mode. I don't know what that is. Usually there's a way for me to change but it looks all right. Okay, so anyway, here it is. R is cosine 2 pi from 0 to 2 pi. And that's what it is. But this program here will let us kind of see how that is happening. So I think I meant to put a D here. I think I messed that up. I don't even know if I can change that. If I hit T, if I put D in there, huh? I don't know. Well, in any case, who cares? Let's go ahead, D. Yeah, that makes sense. N. Well, anywho, it's been a while. So let's go ahead and show you. Polar coordinates are always written in the form R equals some function of theta. So where, like, say, for now, I don't know, what's a good theta? Let's say theta is 90. Like right here, it's 90. If I can get 90, there, oh. You would think I'm not using a mouse. Oh my goodness. Okay, well, you get the idea. Let's pretend we're at 90, and I'm going to take a snip of this, and let's play around with this a little bit. And then we're going to take a look at an equation. Actually, you know what? I don't want to do 90. I think I want something a little bit more, I think I'd rather go 30. There. This looks a little bit better. We can kind of see this okay. We see this okay. Let's get a snip. And I'll show you this really quick. I don't want to spend a ton of time on this, but this is kind of a neat thing. And where'd it go? It's not in there? All right, let's try again. Okay, there it is. And let's see, can we write on it? Looks like we can. Okay. So this part right here, this is what's interesting is, okay, you can see that the radius, what we call each of these little pieces here, is that this is, okay, and apparently I can't write on it. Hold on. This has been an annoying thing for me. There we go. Now I can get rid of this, and we move this over. So let's see, I don't know, can I get it in the same spot? And then now we can hit move this to back, order, send to back, there. Okay. Anyway, this is R, and this right here is theta, and we got a point. Well, a point right there. And so if we're to zoom in on this, we might write something like this. We would say, hey, you know, this is my X and Y axes. Here's X. Here's Y. And here is a line that's connecting to my point. Let's say there's my point, and it's some X. Let's say X naught, Y naught. There's some X, some Y there, right? Now, you could always imagine that right in there, there are other ways to describe this point, and that's what polar coordinates do. Is they're saying, you know what, instead of describing this point with an X distance and a Y distance, where, you know, this is our Y naught, or you know what, I'm just going to leave it X, well, whatever. This is my Y naught, this is my X naught distance, and that's how I get the point. The alternative for polar coordinates is to say, hey, you know what? Let's say we're talking about R, the radius of, and you guys saw this thing float around. I can go back to this. I'm changing theta, and my radius depends on theta. What that radius is how far is it from the point. Now you see right now it's 90 degrees. If we plugged in here cosine of 2 times 90, that would be cosine of 180. That's cosine of pi. Cosine of pi is -1. And so instead of moving up here, because there's my angle, instead of moving +1, I'll go -1, and there's my point. Okay? Whereas here, when it was 30 degrees, that's cosine of 2 times 30. Cosine of 2 times 30, that's cosine of 60. And that would be a positive radius, but it wouldn't be as big as 1, right? Cosine of 0 degrees is 1. And so it's cosine of 2 times 0, still 1. So that's where I am now. And then my cosine's getting a little smaller as the angle gets bigger. Right here at, what, about 45? That'd be 2 times 45, 2 times theta. It says t, but that's theta here. As that that's cosine of pi. Well, cosine of pi is 0, so now my radius is 0, and I'm stuck at the origin here because my radius would be 0. You can play around with this and try to get the idea of how this works. And some of the other videos I posted too, there's some pretty thorough graphing videos. Those might be helpful. They're a little long, but definitely helpful, especially if you look at one starts off with a long explanation, but then he gets into graphing later. You might want to look at that. And I will also post this, and here it is too. Take a look at that if you want to play around with this. That you might find that useful. Anyway, back to this. So I want to be able to, moreover, I explained what r and theta is, but let's go back. So this would be theta here. And just like if we have an x distance and a y distance, we can get to any point. We can also get to any point on the plane if I have a certain theta and a certain radius. I can describe that point that way also. And that's what we call polar coordinates. I could say, you know what, this point has an r and a theta associated with it. And that's another way to describe it. And that's polar coordinates. And often a polar coordinate is written in, like for the one we were looking at, it could have been written as r equals cosine of 2 theta, where the radius changes with respect to theta. Or you could even say the radius part, this distance from the origin, depends on the angle at which we're moving this kind of ray out, all right, from the origin. And, we can go back to Desmos. Desmos is a great example. There it is. It's cosine of 2 theta from 0 to 2 pi. If I just went from 0 to pi, well, I don't have the whole thing, right? I'd start here and I flip around and there I am. I'm there. I got half of it graphed. And you can see, you typed it in just like this. It knows intuitively, oh, that's polar. Can do it. But there's another way to type it in and it would still give us the same graph. And I want to show you that. I do. Yes. And so I'll do that. Let's see here. But first, what would that other way be? Well, I showed you already how you could graph with polar coordinates. And I think that was right here. Did I have another one? I want to say I do. Oh. Maybe I don't. Oh, yeah, right here for my values of t. So I'm going to take this, I'm going to play around with that, and I'll show you how we can change it. Anyway, let's go ahead. First off, how do we relate r theta to x, y? There's lots of relationships here. I could tell you right now, tangent of theta, that's easy. Tangent of theta is y over x. Okay, that's important. Let's see here. Also, I got this other relationship here. X squared plus y squared equals r squared. Oops. And so we got those two. Now let me see, is that useful? What would that help us with? You know what this would help us with? So both of these I can see. What would these help us with? If we have our x and y, if we have our Cartesian, then we can use those Cartesian coordinates to find theta and r. So this would be if we want to go from Cartesian to polar. We could use these equations to help us get there. There's also this other relationship, though, that I care a little bit more about, and that's like, what is sine of theta? Sine of theta, if I'm looking at that, is y over r. Or, more to the point, we could write, and I'm going to use a different color here, we could write y is equal to r sine of theta. And I'm talking about a particular point here. I guess right now, if we're talking about a certain r, maybe I should be using r naught. But for any function with x and y's, right, this would work. So similarly, if I had cosine, well, my x is going to equal r cosine of theta. Now that's really handy. So this I can use if we are going, if I know r and theta, I can get x and y. So this is what we want to use if we're going from polar to Cartesian. Super duper helpful. These are great equations to know and to use. Very, very handy. All right. So we can use those to go from polar to equation. It's not like you have to memorize them. I don't have them memorized. Well, I kind of do. But it's easy enough to draw this little diagram and figure these things out. Watch me do it just now. Now, this, and I want to make another link here. We can take any equation, say like here, r equals cosine 2 theta. Can I write that as a parametric equation? Can I? Well, I almost do. I almost have r as a function of theta. I'm sorry, not r, but right here, you can see I almost have y as a function of theta and x as a function of theta, but it's not. It's a function of r and theta. Because remember, r is changing, and so is theta. R is changing along with theta. X is related to r and theta, and r is changed along to theta. So this is almost almost parametric, but it's not. But I could totally use this to get parametric equations, and that's the cool thing. So if we know this, well, then I know this too. I know that actually, excuse me, then I know that, lost my train of thought. Oh, well, hey, remember what we said. R is a function of theta. Like if you look at this right here, the r equals cosine 2 theta. Well, when we write polar coordinates, or polar functions, I'm sorry, we write r as a function of theta. As we see right here, r is a function of theta. So what we could do instead of writing y is r sine theta, x is r cosine theta, we could say y is r of theta sine theta, or not r of theta, I'm sorry, f of theta. Y equals, instead of r, f of theta sine theta, and x is, instead of r, f of theta cosine theta. Now we have parametric equations. X and y are both in terms of only theta. In our example, so if we wanted to go ahead and do that example, the one I've been messing with, the r equals cosine 2 theta, what can I do? Now this is what's really nice, is you don't have to memorize new formulas in order to do calculus. You do need one. The area one is a little different, but if you want to do everything else, like tangent lines, you don't need a new formula. You just, so for tangent lines, you need derivatives, right? You don't need a new formula for derivative. Use the same one. Just write it as a parametric equation first. And Professor Rob Bob, his examples of doing tangents with parametric equations is very good. And he does use that method. He solves each for x. He writes them like this, and then gets dy, d theta, and dx, d theta. Then he uses the formula. So very, very useful. So here, if I have r equals cosine theta, well, what does that mean? That means, well, x is f of theta cosine theta, or x is r cosine theta. X is r cosine theta, and y is r sine theta. Again, almost parametric, but not quite. But r is actually cosine 2 theta. So actually I could have written this as cosine 2 theta times cosine theta. And here I could write cosine 2 theta times sine theta. And now I have x and y in parametric form. Now I could use all the formulas we have up to this point as they are. All the ones for parametric equations will work because this is a parametric equation. So you don't have to learn a whole lot of new stuff if you don't want to. So anyway, let's double check this. Let's go ahead and plug that into my, well, now we know that's what cosine 2 theta looks like. R equals cosine 2 theta. Let's see if, put it in parametrically, if that's going to work. So my x was cosine 2 theta, cosine theta. So I'm using t instead, so I'll say cosine 2t times cosine t. All right, that's a fun one. And then the other one was cosine 2 theta, so cosine 2t. And then it was sine. R cosine theta, R sine theta. So this would be sine t. You guys ready? Ready? Oh my goodness. What? It's the same graph. It's amazing. Oh, well, this is not going to work now with that because I changed that, but we got the same graph here. If I wanted to copy these in here, that would work. But the point holds is that, check this out. This, especially if I wanted to change this, see here, that is the same graph as r equals cosine 2 theta. Look at that. All right, so I really wanted to show you guys that because that is super handy. Where'd you go? Right here. Super handy. R cosine theta for x, R sine theta for y. And we started off with r equals f of x. In this case, f of x, or r equals f of theta. In this case, f theta was cosine 2 theta. That's all I wanted to show you. You can watch the other videos now that you have this knowledge here. You'll find it very, very helpful. And from now on until that test, we can focus mostly on doing examples in class. Okay? There you go. Hope you guys have a great day. I'll see you tomorrow, maybe.